capitalism.
That's right.
It's not greed. Okay, y'all doing all right? Anyone stay up and watch the game last night? That was an awesome game. All right, well, we need to keep moving along here. Chapter 12, Section 3. I'll probably have another mini exam for you pretty soon. I thought about handing you one today, but I thought, nah, tomorrow's Halloween. Doesn't feel like tomorrow's Halloween. Okay, it is. All right, we're doing double integrals in polar coordinates. So remember what we've established so far is that we can do the volume underneath the surface or between two surfaces so long as the region we're integrating over falls into one of these three categories. It's either a rectangle, which was the easiest case. We could have where our x's are stuck between two constants and our y's are stuck between two functions of x. We could have our y's are stuck between two constants and our x's are stuck between two functions of y. That's what we have so far. So now we want to look at a different type of region that cannot be covered by these three. And it just kind of widens the possibility of what we can integrate over, all right? And it will actually help us, it'll lead us into the triple integral section pretty nice as we move forward. All right, so polar coordinates. You may or may not have seen polar coordinates in Cal 2. I know in my Cal 2 class, if we even talk about it, it's very brief, and it's just because time. So how many of you have seen polar coordinates? A couple? All right. The reason why I don't mind kind of not touching too heavy on it in Cal 2 is because I think at this point you're at an ability level where you can absorb this pretty quickly. Now, you're going to have to go back to pre-cal a little bit here. Remember that if you're given any point x, y in two-dimensional space, there's a corresponding right triangle that goes with that point. So in red, you'll see the standard, what we call Cartesian coordinate system. X, y takes you out to this point, right? But you could also use some stuff from pre-cal, sine and cosine, to determine what the x and y values are. So do y'all remember this? X is r cosine theta and y is r sine theta. You remember that from pre-cal? And you could do that by just, I mean, real quick, if we did sine of theta here, sine would be opposite over hypotenuse. So we'd have sine of sine of theta is y over r, right? And if we just write that down, sine theta is y over r, and solve that for y, we multiply both sides by r, we get y is r sine theta. And you can do the same thing for cosine. All right, so the x-coordinate corresponds to r cosine theta, the y-coordinate corresponds to r sine theta. And what's nice about this is in order to, if you want to move around in two-dimensional space, in Cartesian, xy, right, Cartesian, you need to know two things, don't you? For you to know where this point is, you need to know two pieces of information, the x-coordinate and the y-coordinate. But if you want to use this instead, you still need two pieces of information. You need the radius and the angle, right? So the way I want you to visualize this is you have a person standing at the origin and say, hey, get to this point right here. One approach would be walk parallel to the x-axis by x units, then turn 90 degrees and start walking parallel to the y-axis by a distance of y, and that would get you there, right? The other approach would be stand at the origin and then look out the x-axis, and then I tell you how much to rotate by and then how far to walk out. right? That's the kind of visualization I want you to use. Does that make sense? Okay, now, that is basically everything I just said. We have a relationship that naturally occurs off this triangle, a relationship between the standard Cartesian coordinates and then what this is called, which I haven't named it yet, this is called polar coordinates, right? So we have a connection between the Cartesian and the polar coordinates. The relationships are the Pythagorean identity, x squared plus y squared is r squared. That's one relationship we have, right? And then we can come up with some other relationships. These are the obvious ones. That's from the pre-cal. I just showed you how these two come into play. And then we also have that arctangent of y over x is theta. So looking back at the triangle, tangent of theta is y over x. So if you want to know what theta is, you take arctangent on both sides and you get that last relationship. So these are our standard relationships between polar coordinates and Cartesian coordinates. And we'll be using these. Just remember that. Anytime you see x anywhere, you can always replace it with r cosine theta. Anytime you see y, you can replace it with r sine theta. And we can go back and forth. You can go from polar coordinates to Cartesian and Cartesian back to polar. So now we're going to move forward. Remember what a rectangular region looked like when we started this chapter, right? We said this rectangle R, we wrote it this way, AB cross CD, and what it meant was all the points x, y, such that x was between two constants and y was between two constants. That is a rectangular region in Cartesian coordinates, right? My question to you is try not to reveal the answer here, what would a rectangle look like in polar coordinates? So that would be all of the points r theta, where your theta is between two constants, alpha and beta, and your radius r is between two constants a and b. What would that look like? You have any visual idea of what that would be? Circle. It has something to do with the circle. Let's look at it, okay? Let's actually look at this is it right here. This is a rectangle in polar coordinates. So let's look at our A and B. A and B is our restriction on the radius. So if I change the radius, right, that's going to move those arcs out. You see that? And if I change the angle, alpha, where it starts and where it ends, I could have that right there. That is a rectangle in polar coordinates. And let's just check it. What I'm saying is, this is my starting angle, alpha, right? I want to go from alpha, all points where your angle is between alpha, and swing it all the way around. So this is alpha right here. Beta goes all the way around like that. Oh my goodness. Okay, there's your beta. All right, understand? And then my radius, so my theta is between alpha and beta, two constants. And now my radius needs to be between two constants also. So you can see here this radius right there. That radius is A, and then this radius on the outside right here is B. Does that make sense? So it doesn't look like a Cartesian rectangle, right? If you show that to a kid and, a little 5, 6-year-old and be like, hey, that's a rectangle, they'd be like, huh? Right? This is a rectangle in polar coordinates because your two variables are stuck between two constants. All right. No questions on this region? Could we look at this as a type 1 or a type 2 from previous class? I don't think there's any way you're going to be able to look at this as type 1 or type 2, right? This is not going to be possible for us. Maybe there's ways you could break it up and cut it into little pieces and try and get it, but generally this would be difficult, wouldn't it? Okay. So now what we do is we say, all right, if this is the region, if I want to plug these points, that's what's on the ground, into the surface and figure out the volume below it, right? What would that volume be? What would that integral look like? What would that double integral look like? So I'm going to try and help us build it up. So remember from this formula, and I told you it was going to be very important for us to pay attention to this little thing out here, dA. Okay, what this is saying is we want the volume underneath this function over this region R with respect to area, but that little dA was actually dx dy or sometimes dy dx. And from the picture, here was our rectangle, and the dx was that little infinitesimal width, and the dy was this little infinitesimal width, and what we had three-dimensionally was that little box on the ground, dx dy, and then we had this rectangular box, this parallelepiped is what we called it. Terrible again, just having a good day drawing here. Okay, so there's my little box, and the height of that was the function's value there. So what we were saying is if you take like length times width times height, we get the volume, right? So this part's the length times width, this part's the height. That was the idea, right? Now our picture on the ground is not going to be like this anymore, right? Because when we found the little area here, it was easy. Areas of rectangles, length times width, we're done. But our region on the ground will not look like that anymore, will it? So what would we do here? And you know what? Before I do that, let me do something else. Let me just remind you of something. I just want a clear screen. That's all I want. Okay, so let me remind you of something. This is a formula from pre-cal, recall, that if you have an angle, theta, and you have a radius. So in other words, you walk out a certain distance r, like this, to this point, and then you swing that through some angle theta. Do y'all remember the length of this arc? What that arc's length is? R theta. So S is equal to R theta. Now there is one thing about this formula that you have to be careful with. Theta always has to be in radians. And that is a formula from pre-cal. S is R theta. It's usually in the very beginning of pre-cal we show that formula. And hopefully your instructor in pre-cal or somewhere in your life showed you that if you have a circle, a full circle all the way around, right? That if this is R, if I want to know the distance around it, right, that would be the circumference. Circumference is 2 pi r, isn't it? Yes? But that's this formula right here. Because what's the angle when you go all the way around? 2 pi. So if you just replace that theta with 2 pi r, circumference formula. So the circumference formula actually comes from this formula. All right, we need that because our goal right now is to try and figure out what that little area of our infinitesimal region on the ground is going to look like. So I do my best here to try and show it to you. All right. Imagine, just like we did with the Cartesian, if you cut up the Cartesian into a bunch of little infinitesimal little squares, then that's where we got the little dx dy, right? The little infinitesimal square, or rectangle. Well, when you cut up the two-dimensional plane into polar squares, or polar rectangles, you get a grid pattern that looks more like this. Do you see where this pattern comes from the image I showed you earlier? Yes? So if we want to say, hey, what does a little rectangle in here look like, a little infinitesimal one? Well, this length right here is the easy one. This right here is our little change in radius, right? That's the change in the radius of that little region. So we'll call it dr. Instead of dx, dr. That fair? Yeah? Yeah? Okay, and then what we need to do is we need to figure out what the area of this red thing would be. Now, what would that area be? It's almost a rectangle, right? It's not quite. But remember what we do with the integral. We're going to cut this into to smaller and smaller pieces, right? So right now, if I tried to draw a traditional rectangle in here, like if I connected these and I drew like a true rectangle in here, I would probably have some error there, wouldn't I? I would have some error. That error would be right in here. Do y'all agree? But if I make this smaller, right, cut it into tinier and tinier, tinier and tinier pieces, this error gets smaller. And when you do an integral, you're cutting it up into an infinite number of pieces, so that error goes to 0. So what I'm trying to say is that the area of this red is definitely not, this is not a rectangle. But in the limit, when you apply the limit through the integral, the area of this basically becomes the area of a rectangle. So what I need to figure out is this side times this side. This side, the best way to estimate this side, because it's a curve, is to use S, the arc length, that length right here. Okay, so the picture I drew a second ago to recall from pre-cal, that's this picture right here. All right. This is R, right? The distance from here is your radius. And then this right here, this angle you're sweeping through, is your change in your angle, your d theta. So if I say this right here is d theta, and this is R, then this arc length is, where did I put it? I didn't put it in. Oh, here we go. It's right here. Then that little piece right there would be the radius times d theta. Y'all buy this? Okay, so the area of this red thing, the dA, the little infinitesimal area on the ground, is now going to be approximated with, or given to us by this formula here. Here's the S, that's this piece, and then, no, circled the wrong thing. The RD theta, right, that piece is this side, and then dr is this side. So if you multiply all those together, you should get the area in the limit, right? In the limit, that's going to give you the area. So r, d theta, dr. And these two, again, they can switch places. The order of integration can switch depending on the problem. All right, that's it. That's the geometric setup to what's happening. Now let us come up with a final formula. So this is the part that matters. If you are doing a double integral in polar coordinates over a polar region, where your region is given by r theta, where your theta is between two constants and your radius is between two constants, then the double integral, right? The area, the volume underneath the function over that region R with respect to area is the integral from a to b. That's your outer integral. And notice that a to b, the outer integral is dr because r is, the radius is changing from a to b. Then your inner integral goes from alpha to beta, and then it's d theta is on the inside. And then f of, what the heck is this? F of, what's that? Yeah, that's our function, but replacing x with r cosine theta, and then y, right? And then this, right? That r, where is that coming from? That's what I was trying to get you to see right here. This dA does not just become dr d theta. What does it become? R dr d theta. And so anytime you go from Cartesian to polar, you are always going to have to introduce an r into the integral. And I've highlighted it, and I've said it here because this is the part that students forget. But y'all aren't going to forget, because remember, we're going to do the whipping now, the corporal punishment for forgetting things like that, right?
Was there an extra credit for today?
Extra credit? All I remember about last week is that I said today I was going to start randomly hitting people with the stick.
No, you said you were going to ask us a question.
It was a specific question.
If you got it wrong, you were going to start hitting everybody.
It was a simple question, right? Do y'all remember the question? Okay, if you don't remember the question, everyone gets 3 licks. Okay, so the double integral, how do you get the volume of the, how do you get the area of the region from a double integral? You integrate what? What function? The 1, right? How was it? Okay. All right, let's not lose focus here. When we go from Cartesian to polar, you must introduce an r, all right? That's what we have to do. Now, later on, as we progress through this class, especially when we get to triple integrals, we're going to go from Cartesian coordinates to cylindrical coordinates, and we're also going to go from Cartesian to spherical coordinates. And we're also going to do something where you just change the variables, which is basically a conversion from one system to another. And anytime you do that, you're always going to have something pop out here. There's always going to be something here that we're going to find, and it's actually called the Jacobian determinant, but that's later. We'll do that later on in the class. All right? We're actually going to have a formula, and I will show you where that r comes from in a formula later. I tried to show it to you geometrically, but we'll have a nice formula to get it later. All right, first example. Find the volume under z equals 3x plus 4y squared on the region bounded by this, with y being greater than 0. All right, so we have some surface here, right? This is our surface. And we want to know the volume below it, where our region is in two-dimensional space, bounded by this, and y is always bigger than or equal to 0. So what is this in two-dimensional space? Circle, radius 1, circle, radius 2. Y is greater than or equal to 0. Let's draw that. Circle radius 1, circle radius 2. It's the region bounded by both of those, but also y has to be bigger than or equal to 0, which means we're only talking about the top half of this, right? We're only talking about this region right here. That's the region of integration. Now, is that a rectangular region in Cartesian? Is it type 1, is it type 2, or is it polar? Well, it definitely is polar, right? Could you do this with a type 1? Do you have your x between two constants? No. You would have to break this up. If you looked at the right side, you would have to do like from here to here, you have this function on top, this function on the bottom. That would be a type 1. And then when you get from 1 to 2, it would be this curve over 0. So you would have function on top and bottom. So you could break this up into 4 separate regions. Do y'all see it or no? You could do 4 separate type 1 regions. And that would suck. What's that?
I said you could do type 1 and type 2.
You could also do type 2. You could look sideways and you could break it this way. So you could do type 1, type 2, but who wants to break it up like that? Especially when this is a very nice polar region. So in terms of a polar region, all you have to do is give me restrictions on theta and r, and I'm in business, right? So what is your theta restricted between there? 0 and pi. And what is your radius restricted between? So you always want to be between here and here, right? So 1 and 2. That's a rectangular polar region. It's very straightforward, right? Between two constants. Isn't that easier to work with than if we did type 1 and type 2? You would actually have to find equations for these circles, solve for y, and you'll have roots, and oh, it'll be really kind of messy, won't it? Okay, so I'm going to try and set up this double integral. I'm going to say double integral Now, just like it was with rectangular regions when we were doing, not type 1, the one before that, the order of integration didn't matter. Same thing here. If our two variables are between two constants, then our order of integration will not matter here. So let's go with theta first. We'll go 0 to pi. That means the outside is going to be d theta. The inner integral will go from 1 to 2, and that means this will be dr. Okay, yeah, I'm going to put the r in there, all right? Just not yet. I will put it in. Now, what goes in the integrand? What are we integrating? What's the function we're trying to find the volume under? This, right? Okay, so solve for z. We need this in here. However, we've gone from Cartesian to polar. So we can't put x and we can't put y. We have to replace x with r cosine theta, and we have to replace y with r sine theta. So this is going to be, I need a little more room, sorry. 3x, so 3, what? R cosine theta plus 4, and then y is being replaced with r sine theta. So r squared sine squared theta. Does everyone see that this is x plus 3x plus 4y squared? And then we have out here dr d theta, but we have to put in the r. Do not forget the r. So I'm putting it in red so you don't forget it there. The r goes in by default every single time, dr d theta. And now this is just an integral, right? Double integral. So let's go ahead and let's pass that r through, right? Because that r distributes through to everything. So I've got integral 0 to pi, integral 1 to 2. I'm going to be integrating 3r squared cosine theta plus 4r cubed sine squared theta dr d theta.
Wait, the 3 is excluded.
The what?
The x value.
Which one?
Oh, never.
Yeah, just the r cubed and then sine squared still. Could I split this into two separate integrals? Yes. Okay, now I'm not going to do this, but I could, right? I could split this into two integrals. If I split this into two integrals, on this one, let me just show you what I could do. I'm not going to do this. I don't know why. I don't like doing this, but I want to show you what you could do. My first integral, if I split it, would be this. And then I have plus, I have the other integral over there, right? This one, because I'm missing my dr d theta, plus now my other integral. If I did this first one, because the two variables are separated from one another, right? There's not an r inside the cosine, there's not a theta out here. Because they're completely separated by a product, I could use a property that I showed you all last class where I could turn this into integral 0 to pi of what though? Cosine theta d theta times integral from 1 to 2 of 3r squared dr. And then plus, and then I could split the second one up the same way, couldn't I?
Yes.
Okay, I'm not going to do it that way, but I just want you to be aware the book does it this way. All right, so if you're looking through like a solution manual and you see them do that, that's what they're doing. I just go ahead and integrate it. Like at this point, I say, all right, integral 0 to pi. Okay, here's my inner one. I'm going to integrate this and this both with respect to r first. So cosine theta is a constant. 3 is a constant. So I just ignore the 3, ignore the cosine theta. I integrate r squared, which is going to be 1/3 r cubed. And that hits that 3. So just r cubed cosine theta. Agree? And then what about the next one? Ignore the 4, ignore the sine squared theta.
Yeah, the 4's going to cancel.
You're going to get 1/4 r to the 4th. So the 4's are going to cancel. You just get r to the 4th sine squared theta. And then you have to evaluate this from r equals 1 to r equals 2. And then we'll do d theta afterward. So if we plug in 2, here's my integral, 0 to pi. I'm going to plug in 2 first. So what do I get when I plug in 2 for r? 8 cosine theta plus 16 sine squared theta. And then minus, subtract from that, plug in 1, I get cosine theta plus sine squared theta. And then close that out, d theta. Are y'all with me on that? I can combine some like terms together there. I'm going to have 7 cosines, and I'm going to have, what, 17 sine squareds? 15, sorry. Integral 0 to pi of 7 cosine theta plus 15 sine squared theta d theta, which equals 7 sine theta evaluated from 0 to pi plus 15 integral from 0 to pi of sine squared theta d theta. So I went ahead and took care of the first integral because the antiderivative cosine is pretty straightforward, right? So that's just this. I'm going to evaluate it at pi and at 0. What am I going to get when I do that? Sine of pi, 0, and 0. So I just get 0 from this. So that's just going to be 0. But I need to integrate that. So how do you integrate sine squared? Power reducing formula. I can rewrite the inside of that. So this is gone, right? That's going to be 0 minus 0. I'm gone with that. So this is 15 integral 0 to pi. What's that power reducing formula? What does this turn into, sine squared?
2 sine cosine theta?
It's,
Is that like what
it's 1 minus cosine 2 theta over 2. Or you could write this as 1/2 times 1 minus cosine 2 theta. This is our power reducing formula. I actually taught that last week in pre-cal. I was like, y'all better remember this. You need it in Cal 2. You need it in Cal 3. So that's our power reducing formula. Do y'all remember that in calculus 2, where you had to like integrate like sine to the 6th theta d theta? So you had to do like power reducing. It started to like, you almost had to like turn your paper sideways to get it all on one page. Yeah. Fortunately, we only have one power reducing to do here. But okay, so that's going to become, I like to use this one. In Cal 2, this is the version I like to use. So I pull the 1/2 out, that becomes 15 halves. And now I'm integrating 1 minus cosine 2 theta, d theta. And now I can integrate. So when I integrate this, I get 15 halves. Antiderivative of 1, theta, because you're integrating with respect to theta. And then antiderivative of cosine of 2 theta. So we'll have minus 1/2 sine 2 theta. And we're evaluating this from 0, oh no, not from 0. What is my, 0 to pi, right? What's going to happen in this part when I plug in pi? Sine of 2 pi is 0, right? 0 in here, sine of 0 is 0. So that part's not going to matter, is it? Pi into here, just get pi. 0 into here, 0. So my answer should just be 15 halves pi. All right. This okay? All right, I think now would be a good time to do something kind of cool. I think it's cool. I don't know if it's cool. I mean, I know it's cool. I just don't know if you all understand what cool is. All right? So let me see. Show the area of a circle, radius capital R is pi capital R squared. Now we all know that. We all know that the area of a circle is pi r squared because someone told us that once, right? Yes? Okay. Let's draw a circle of radius capital R. We want the area of this, right? What was your name, sir? Justin? You suggested earlier that the area of a region is equal to the double integral of 1. Is that what you were saying? Something like that? Yeah, we said from last class, this was the thing I was supposed to whip you all over the head about. The area of a region, I'm going to call it D so you don't confuse it with the radius. Region D is equal to the double integral over D of 1 dA. That was from last class. Do you all remember this? And I was saying because if we look at the function as being 1 unit high, then the height is equivalent to the area because you're multiplying by 1, so it's the same thing. Let's use this. If I want to know the area of a circle, right, I'm going to let that region on the ground be a circle, and I'm going to do the double integral of 1. But look at your circle on the ground. If that's our region, that's a great polar region, isn't it? It's a really good polar region. What is this as a polar region? What's my theta and my r restriction? 0 to pi, and then what's my radius restriction? 0 to capital R, right? That's my radius restriction. Understand that? Yeah? Okay, let's set up this double integral. But I'm doing it in polar. So I'm going to go integral, let's go 0 to 2 pi. Let's go 0 to capital R. And what am I integrating? 1. And then R, good. R because I'm doing polar, right? R, and then dr d theta. All right, this is going to go really, really quick. This is the function we're integrating. We're doing it with respect to r. What's the antiderivative of r? 1/2 r squared. So 0 to 2 pi. This is going to be 1/2 little r squared. I'm evaluating from what? Little r equals 0 to little r equals capital R, right? D theta. What happens when you plug in capital R? You get 1/2 capital R squared, right? When you plug in 0? 0. So now what you get is integral 0 to 2 pi. And what did we say that was? 1/2 capital R squared? I'm going to pull the 1/2 out. And now I'm going to integrate with respect to theta. All right? Well, capital R, I could have pulled that all the way out, couldn't I? That's a constant, capital R?
Yes.
But I'll leave it there. What's the antiderivative of capital R squared with respect to theta? Just capital R squared times theta. So this is just going to be 1/2 capital R squared times theta. And where am I evaluating this from? 0 to 2 pi. What happens when you plug in 2 pi? For theta. You get pi r squared. What happens when you plug in 0? 0. This is pi capital R squared. There we go. That's pretty cool. That took about, what, 2 minutes? I think in my Cal 2 class I proved pi r squared is the area of a circle, but it requires trigonometric substitution, and it takes a while. With polar coordinates, it's almost kind of, this was easier to do than the previous problem, I think. So very nice result, changing coordinate systems. That's why changing coordinate systems is useful, because you can take a problem that's pretty complicated in Cartesian, switch it over to polar. Yes.
So this is going to make that problem with like the cylinder and the sphere, it's like super easy.
Which cylinder and sphere?
Like on the quiz that we have?
The take home, I don't know. I'd have to look at it again. It could possibly, yeah. I didn't write that test with polar in mind, so I haven't looked at it from my polar goggles. So maybe I'd have to look at it. Yeah, but you're kind of making my point a little here. This is good. We have different coordinate systems because sometimes the problems are easier in other coordinate systems. And that leads me to something else. You were shown that in college algebra, right?
Yes.
And you were shown complex solutions and like that. But since then, have you seen it again? Like, where have you dealt with it?
Physics.
In physics? So you're using imaginary numbers in physics? Why? Is it like fake answers or something?
No.
Are they like imaginary answers?
Kind of. We have to use the polar coordinate system. So we
Oh, you use I to use polar. You do the like Euler's formula to. Okay, so the reason I'm bringing this up is because you're introduced to the complex numbers at a point in college algebra, and then after that you don't see them again. All right. And the reason you don't is it's a long story, but it's because it's difficult to visualize them. And functions that deal with complex numbers are four-dimensional, like 2 dimensions for in, 2 dimensions for out. You can't see them. It's difficult. So you have to be a more advanced state of mind to start studying this. But the imaginary numbers, the complex number system, is, I'm trying to convince you that going from Cartesian to polar makes problems easier sometimes. If you just live in the real numbers, if that's all you ever learn and you try and go do engineering and do a bunch of different applications as you progress on, and that's all you know, you're going to run into some problems that are very difficult, that you have a trouble solving. But if you understand that the real numbers actually live inside of a bigger system of numbers called the complex numbers, then if you look at the problem from the complex numbers perspective, the problem can become easier. And that's why complex numbers are important. It's because it's another perspective that you can use to solve a problem. And I'll give you a very simple, not a simple example, but if you saw this integral in calculus 2 ever, then that means you have to integrate along the entire number line, right? And that means you're going to have to do some limits and figure out what happens. If you are doing this in complex numbers, like you're allowed to use complex numbers, then you can change this integral into integrating over what we call like a closed loop. You can turn an infinite number line into a closed circle, which is weird, but you have to be able to look at it from the perspective of complex numbers. So lines, infinite lines, become circles in the complex number system. And so it's much easier to integrate over a circle, which we haven't done. We will do this. We won't deal with complex numbers, but we will integrate over loops. It's easier to integrate over a loop than it is to integrate over the whole number line, sometimes, okay, sometimes. So I remember very vividly a point in time when my brother's an electrical engineer, he's younger than I am. So when he was finishing up his bachelor's at Boston University, he was doing a problem that he and his classmates were having a lot of trouble with. At that time I was in graduate school, and he gave me this integral. And so the first thing I did is I took it over to complex numbers, I turned it into a loop, and then I integrated it and I gave it back to him. It took me like 5 minutes. And he's like, well, we've been working on this for weeks and all this stuff. And then I showed him the math. He's like, what is that? So he hadn't even dealt with the complex numbers to that level where he was using it. So what is my point? My point is polar right, is useful to make hard problems in Cartesian easier, but that I, imaginary number, that we're raised to believe it's not useful, is very, very useful later on. Mathematicians, we use complex all the time. So don't think that the I is imaginary. Like, it gets a bad rap, doesn't it? Don't imaginary numbers get a bad rap? It's like, hey, I've got my imaginary friend on my shoulder here. Like, I'm a weirdo as soon as I start talking like that, right? But that's the way when they first started talking about the square root of -1, everyone was kind of like, hey, that guy over there that's talking about that, he's a little bit off the wall there. Let's imaginary numbers. Later on, it was proven that these things are valid. So, but you can't change that first impression, All right, I went off on a tangent there. I apologize. All right. Oh, did I scroll down? Okay, so we've got that one. And we proved that the area of a general circle is pi r squared. Don't do that every day. All right, find the volume bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So to do this problem correctly, you kind of have to have an idea of what this looks like. So let's try and graph this kind of, all right? Let's kind of graph this. So to get a good point on this, how about we plug in 0 for x and 0 for y? What would our z value be? If x is 0 and y is 0. 4. So at the origin, I go up 4 units. I have a point right there, right?
Yes.
Okay. Now, what if z is 0? If z is 0, what I'm saying is, where does this surface hit the xy plane?
2.
So if z is 0, what does that equation turn into? 0 equals 4 minus x squared minus y squared. If you move the x squared, y squared to the other side, you get x squared plus y squared equals 4, which is a circle radius 2. So 2 out, 2 out. And this thing is a paraboloid. Looks like this. It's like a bowl turned over or something like that. We want to know the volume of that. Which means we want the volume under this surface, don't we? Under it, down to the xy plane. What is the region we're going to integrate over? The circle, right? This circle right here. So our region on the ground, this right here, this is our region on the ground. That region is a very nice polar region, isn't it? Theta's between 0 to pi, and the radius is between 0 to 2. I have a question. Could you do this? We haven't discussed this, but could you do this? I'm just wondering what your thoughts are here. Would that be the same region? Is that the same region as that?
No, wouldn't you have to multiply by 2?
So let's see. If I start out at 0, this says my radius can be between what?
-2 and 2.
So if my angle is 0, I can walk out 2 this way, and I can walk out 2 backwards. Now change my angle a little bit, and my angle can go between 0 and pi. So let's say I change it to here, like right here. Then I can go out 2 and backwards 2, right? Or if my angle is right here, I could go out that way 2 or backwards 2, right?
So you don't have to do the full circle, you can just do...
That's what I'm asking you. Do you think this would work if I go out this way, out that way, and then out that way, out that way, and out that way, out that way?
Yeah, it would work.
Yeah, as long as I go from 0 to pi, this works. I will fill the whole circle in. That does work. Now, I won't ever do this, but just so you see, that could be your limits. If you go from 0 to pi, that's no good, because you basically draw the circle twice, right on top of itself. All right, that's off topic, sorry. Not off topic, but random. All right, double integral. Go from 0 to 2 pi, go from 0 to 2. I'm integrating that, right? And so I need to solve it for z, which it already is. And then I need to replace x with r cosine theta and y with r sine theta, right? But what's even better than that? Do you agree that that's this? What is x squared plus y squared when you convert not when you convert to Cartesian, from Cartesian to polar? R squared, isn't it? R squared. So that right there is actually 4 minus r squared. And then I need another r. No, I factored out the negative, right? If I factor a negative out, then it becomes this. And then this part right here is r squared. So if one of these was negative and one was positive, you couldn't do that. It's only that they're both positive when you pull the negative out.
It's just r squared because it's the identity, right?
Yeah, remember the triangle we drew? This was x, this was y, and so this was r, you know? X squared plus y squared equals r squared. Okay. And then what, dr d theta? I don't think I'm going to work that one out. That's super clean, right? R goes through, integrate with respect to r, plug in, theta, done. We good? All right, this next one, this is just saying that if you have a region on the ground and you have two surfaces and you want to find the volume between them, it's the same thing we did before. You take the surface that's on top minus the surface that's on bottom. You still convert it over to polar regions, but you subtract the two integrals. So that's nothing new. It's just our region on the bottom looks different. That's all. Pardon? Let me do this example and I think it'll become hopefully more apparent. Find the volume of the solid below x squared plus y squared plus z squared equals 1 and above the cone z equals the square root of x squared plus y squared. So do y'all know what x squared plus y squared plus z squared equals 1 looks like? It's a sphere, right? Unit sphere. That's x squared plus y squared plus z squared equals 1. All right, how about the cone z equals square root of x squared plus y squared? Well, it's a cone, so it's kind of already given away, right? Do you agree that z is always positive? except 0. Z could be 0, couldn't it? Where would z be 0? At the origin, right? So I actually know that this point right here is on my cone. But because it's the square root, I can only have positive numbers come out of this, right? So it's a cone that should open upward like this. Right? Like that. We want the volume that is below the sphere, so within the sphere, but above the cone. Do you all see the solid? Do you all see it? Inside the sphere and above the cone. So right now, if I put my hand inside that cone, my fingers are above the cone. If I'm down here, this is below the cone.
That's going to be like a weird cone art thing.
So kind of like this piece right here. Right there. Kind of like that thing. Do y'all see that? That's what we want the volume of. That green sucks, so I'm going to use a different color here. That's not a very good picture, but it's like a little ice cream cone. Not a very tall one here, but we want the volume of this. Do y'all understand this? Do y'all see it? Visualize it?
It's like one of those
Yeah, the ones with the little igloo, right? When back in PE or something, right? You pull the little thing off. All right. Do you have a top surface?
Yes.
Do you have a bottom surface?
Yes.
Okay, what's the top surface? The sphere. What's the bottom surface? The cone, right? So if can you solve this for z?
Yes.
That would give you the function for the sphere. Now it would only give you the top half because you have to solve for z. You have to take a square root, don't you? Okay, so let me label this one as our top function. So I'm going to call it f of xy. This would be equal to square root of 1 minus x squared minus y squared. So I just moved x squared and y squared to the other side, took the square root. So that was me solving for z, right? This is my top function. Now the bottom function, g of xy, is the cone solved for z, but it already is. Any questions so far? Top and bottom. What do I still need to resolve? What do I still need to figure out?
The restriction.
The region.
Yeah.
So this is the big question now. What is the region? It's on the ground, right? It's on the xy plane.
Could you go from 0 to pi, or 0 to 2 pi?
0 to pi all the way around.
Yeah, since it's on the ground, it's a two-dimensional circle.
Is it a circle?
I would think so.
Okay. Yeah, but what's the radius of the circle?
1. Well, because if you eliminate z is 0.
Don't I need to look at this from straight on top? If I look straight down on that, right, I'm going to see the ice cream cone. I'm not going to see this point. And I can imagine that it's going to project almost like a shadow down onto the ground, right? And that shadow down onto the ground is my region of integration. Do you all see that? That means you need to figure out where they hit each other. I need to actually figure out where do these things hit each other, right? So that I can figure out how big that radius is. Yeah?
Wouldn't you have to figure out the radius of the cone?
But see, well, you can't figure out the radius of the cone because the cone keeps going out, right? So this radius is always changing. The thing is, where does it actually punch through the sphere? Because when it punches through the sphere, that's where we have the
So it's
cone
actually
part.
less than 1.
It's got to be less than 1 because we know that the radius of the sphere is 1. So it can't be 1. Can't be bigger than 1 either, right? So it's got to be smaller. So just like we've done in the past, you set the two equal to each other, right? So let's set f and g equal to each other. So where does f equal g? Something in this equation is going to tell us the equation of that sphere. I mean, this circle. So when we set them equal to each other, we get root 1 minus x squared minus y squared equals root x squared plus y squared. We square both sides? Okay, if we square both sides, we get 1 minus x squared minus y squared equals x squared plus y squared. Let's move our x's and y's to the right and divide by 2.
1/2.
So this is the equation of a circle, isn't it?
Yes.
What's the radius of the circle? Radius is root 1/2, right? Because remember, that's r squared. X squared plus y squared equals r squared. So just the square root of that. And you could rationalize this if you wanted to. I don't care if you do. But that's the same as root 2 over 2.
That would be little r, right?
That's little r. That's the range that we have. So this region on the ground is a polar region. We can say its theta goes between 0 and 2 pi. And we can say that the radius goes between 0 and... You want root 2 over 2 or 1 over root 2? Do you care?
Root 2 over 2.
You want root 2 over 2? Any questions on this?